Let's do problem number 17 in chapter 4 on page 102. And I will read the problem first. Here it is, 17. It says, a ball is tossed from an upper story window of a building. The ball is given an initial velocity of 8 meters per second at an angle of 20 degrees below the horizontal. It strikes the ground 3 seconds later. How far horizontally from the base of the building does the ball strike the ground? And B, find the height from which the ball was thrown. And C, how long does it take the ball to reach a point 10 meters below the level of launching? Okay, so this is a lot of work. So I went ahead and got it ready in terms of given, find, and solve. So let's go over what's given again. The ball is moving 8 meters per second, 20 degrees below the horizontal. So it's kind of at an angle like that. And it hits the ground 3 seconds later. We want to know how far from the base of the building does it hit the ground, at what height, and this is delta y. Okay. And then how much time does it take for it to go down 10 meters below where it was thrown? So that's our problem. So let's figure out, let's do part A. Okay, now delta x. So let's start with what we're trying to find. There's only one kinematic equation when we're doing projectile motion problems in the x direction, and that's v naught x times t, right? So because there is no acceleration in the x direction in projectile motion problems. The only acceleration is that of gravity down, which is 9.8 meters per second squared down, so it's negative. But anyway, in the x direction, we have this. Now, we need v naught, so we can say, well, delta x is equal to v naught x, and v naught x is 8 meters per second times the cosine of, and this is really negative 20 degrees. Doesn't matter for cosine though, does it? And then times time, and we actually are given time. This is kind of a weird problem because usually we have to solve for time or substitute for it. But here they gave it to us. It's going to be 3 seconds. So when you go 8 times the cosine of 20 times 3, what do we get?
7.5.
What is it?
7.5
7.5?
and then times 3. So altogether, they will have
Really?
2.4.
Oh, yeah. I mean, 7.5 is the velocity in the x direction.
Yeah.
And then you multiply that by time. I'm just going to go for the whole calculation here. 22.4 meters. Okay? So, again, from a problem-solving approach, I write out given, find, and solve. Start with what you're trying to find. You know, there's only one expression for delta x. And then you go, oh, well, I know everything that I need. So there you go. You do have to draw the problem very carefully and remember that the velocity in the x direction is a component of the initial velocity, not the whole. So if you put 8 meters per second instead of 8 meters per second cosine 20, you're going to get the wrong answer. Now, for delta y, let's do the same thing. Delta y is equal to v naught y times t plus 1/2 a t squared. And again, I know time, I know the acceleration, I know I can figure out the initial velocity in the y direction. So this is going to be, and let's do this in pieces so that we can see clearly what we're doing. V naught y, well, that's v naught times the sine of the angle, negative 20 degrees. And so this is, and this is 8 meters per second. So what do you get when you get 8 meters per second times the sine of negative 20? What do you get? 27 point, no. I'm just 8 times.
Oh, 52.32.
No, the v naught y. It's 8 meters per second.
Isn't it 27.4? Negative 2.7.
Well, think it's got to be way less than 8, right?
Put 80.
Oh, you put 80. So move the decimal over. What do we get?
2.74.
What is it?
2.74.
2.7. That makes more sense. 2.74
Yeah.
meters per second. Now, here's what a mistake a lot of students will make. They'll either forget the negative 20, the negative in front of the 20, and so they'll write it down as 2.74, and that'll get you the wrong answer eventually. Or, now if you use 20, but you look at the picture. Look at the picture. The initial velocity is obviously downwards, right? It's thrown down. So you can just stick the negative in there if you know that it's down. And we know what the acceleration is. So I think we're just ready for delta y. Now delta y is equal to negative 2.74 meters per second times 3 seconds plus 1/2 negative 9.8 meters per second squared times 3 seconds squared. And when you do all this arithmetic, what do you get for delta y?
You get 52.32.
Negative 52.32?
Yes.
Okay, did you check that? Does that
Yes.
jive with what the book said in the back? Okay. Meters. Now, notice that it says delta y is negative, because this is a negative quantity, and this is a negative quantity. You add them two together, you get this. Very good. Okay, but it wants to know how high is the building. So remember that, okay, the building is 52.32 meters high, because the ball fell, or not the building, but where the ball was thrown. Since it fell 52.32 meters, we can say that the height from which it fell, I'll just call that h or whatever, is 52 point, and I'll just round it off to 3 significant figures. And there we go. Okay? So, you have to think, I know you were worried a lot about, like, when do you stick the negative in and when do you leave it. Remember, you can think during these problems. You can really think. You can say, okay, this is falling down, so this initial velocity is negative. Delta y is negative. The ball falls down, so it fell down by this, so that means the height is, 52.3 meters high. You can just say, hey, just drop the negative. Oh, that was B, wasn't it? Yeah, let's put B right there. Now C is a little bit trickier. Now we're trying to find time. So I don't think I need A and B at all, so I'll just cover it up with this paper. So let's do part C. And what do we know? Well, we're given that delta y equals negative 10. So I have delta y, and I'm solving for time, and I know the initial velocity in the y direction. So v naught y times t plus 1/2 a t squared. Okay, so now what I'm going to do is plug in our values here. This is negative 10 meters, right? It was given that the ball, or whatever it was, fell down 10 meters. So delta y is negative 10 meters equals, and what was v naught y? Negative 2.74 meters per second times time. And then this is plus, and what is A? A is negative 9.8, and so 1/2 of that is negative 4.9. So I'm just going to go negative 4.9 times time squared. Well, what am I going to do?
I plugged it into my solver.
Ah, yes, you plug it into your solver. So negative 4.9 t squared. I'm going to drop the units, which I don't like. This should be meters per second squared here. Then minus 2.74 times t plus 10 equals 0. Now, if you want, if you don't know how to use your solver button, you can use the quadratic formula, which is a big pain in the you know what. But you guys have those fancy calculators for a reason. Now, when you plug this into your calculator and solve, what do you get for time? You should have gotten 2 answers.
I got 1.17. Or 1.18.
1.18?
Yeah.
What was the other answer, though?
I don't know.
Right. It gave you a negative answer, didn't it?
No. Negative.
Yeah, it did.
There is negative 1.75.
1.5?
Negative 1.75.
1 point. So it'll give you a negative 1.75 when you plug this into solve. Now that actually makes sense because, okay, what is this negative root here? They're called them roots, right? When you solve a quadratic, equation like this, they're called, because, okay, where's negative 10? This is about 50 something, so negative 10 is right about here, right? So in 1.18 seconds, it's going to fall from here to here. But if you go negative 1.75 seconds, it'll be over here. See, this is kind of, if you launch it, what if you didn't launch it from, what if somebody threw it from inside the house or something, or this is a big warehouse or something, and you threw the ball, and the ball, went up and then down this way. So there's a time before t equals 0 where the ball was at negative 10 meters. Now, of course, in this situation, the ball was not in flight at that point. We threw the ball at t equals 0, so this is meaningless.
Okay.
But that's what that root means, okay? Does that make sense?
Yeah.
So our answer is that. Okay? Let's see if we can get the whole thing. Let's get the whole thing. And that, oh yeah. And that is problem 17. That is all.